Hello, this is Professor Matt Katroulis, and this is the first video lecture for Chapter 3 on ionic and covalent bonding. This is for Chemistry 110, Chemistry for Allied Health Majors. The last thing we talked about in Chapter 2 was the valence shell and the valence electrons, and so this next subject, the Octet Rule, flows naturally from that. The Octet Rule tells us that many atoms are going to react in a way so that they have 8 electrons in their outermost energy level. That's also recalled their valence shell. If you remember, group 8A, the group on the far right of the periodic table, are the noble gases. And those elements tend to be the least reactive of all elements on the periodic table. And a lot of it has to do with the fact that their valence shell is completely filled with 8 electrons. Helium is a bit of an exception in that it has 2 electrons, but helium behaves just like the other noble gases in being very stable and very unreactive. It's important that you understand that those two words mean essentially the same thing for us: stable and unreactive. So atoms which might be less stable, like say a sodium atom, or say a chlorine atom, will gain or lose electrons until it can get to 8 electrons in its valence shell. And in that way, it becomes much more stable compared to the way it was before that change. So there's a couple ways in which an atom can obtain an octet. With metals, they tend to lose the valence electrons, and that gives them an empty outer shell. And that means that the next shell in becomes the valence shell. I'll show you this in a moment. And that valence shell would be full with all of its electrons, and so you would have achieved an octet. Nonmetals, on the other hand, will gain electrons, or they will share electrons to get to 8 electrons in their outer shell. When nonmetals are reacting with other nonmetal atoms, they will usually share. And if nonmetals are coming together with metals, the nonmetals will take away the valence electrons of the metals. So let's look at how this might work out. Sodium has this electron configuration here: 1s2, 2s2, 2p6, 3s1. The valence shell for sodium is 3. That's the highest shell out, 3. Chlorine also has a valence shell of 3, but it has 7 electrons in its valence shell. Remember, we could just easily find these numbers by looking at the periodic table. Sodium is in group 1A, so it therefore has 1 valence electron. Chlorine is in group 7A, so it has 7 valence electrons. Sodium would really like to lose 1 electron, and chlorine would really like to gain 1 electron. Because after that fact, I'd like you to look a little bit closer at this picture here. Well, once this electron is gone, shell 3 is empty. If shell 3 is empty, it can't be the valence shell anymore. So now shell 2 is the valence shell, and it has 8 electrons. We call that having an octet. Chlorine gained that 1 electron from sodium, and now in shell 3, its valence shell, it has 8 electrons. And so ultimately the situation on the right, where both of these atoms have octets, is much more stable than the situation on the left. And in fact, if I reacted sodium metal with chlorine gas, they react extremely violently as the electron flows from sodium over to chlorine. So what I'd like you to do here is I want you to look at these elements here and predict how many electrons will be gained or lost by each of the following atoms. Let's just do a practice here. So if we look at bromine, let's go find it on the periodic table. So it's right here. It's in group 7A, and it's a nonmetal. So nonmetals, remember, gain electrons to get to an octet. Bromine has 7, so it's going to need to do what? It's going to need to gain 1 electron. And once it's gained 1, it now has a full octet. Let's do one more practice together. Barium. Barium is right here, element number 56 on the periodic table. It's in group 2A, and it is a metal. Now, metals lose their valence electrons, we saw. So barium has 2 valence electrons, so what's it going to want to do? It's going to want to lose 2. So gain goes with the nonmetals, and lose goes with the metals. So I'd like you to pause the video for a moment and figure out what each of these elements are going to want to do. And then unpause when you're ready. Okay, let's continue. Potassium is a metal. It's in group 1A. It's a metal, so it's going to lose valence electrons. If it's in group 1A, it has only 1 valence electron, so it will lose 1. Aluminum is in group 3A, right here. It's a metal, so it wants to lose its valence electrons. Since it has 3 valence electrons, it will lose 3. Oxygen is a nonmetal. It's in group 6A. Nonmetals want to gain electrons. So to get to 8, 6 needs to add 2 to get to 8. So it's going to want to pick up 2 more electrons. So it will gain 2. Now neon is a noble gas. It's in group 8A. And so what's it going to want to do? Well, it already has an octet, so it will do nothing. It doesn't want to gain electrons or lose them. It already has an octet, and consequently, it's not going to react with other elements. It's a stable atom. I mention here the Duet Rule just in passing, which has to do more with helium and the elements near helium than any of the others. Hydrogen has only 1 valence electron, and the nearest noble gas to hydrogen is helium, which has 2 electrons. So rather than trying to get 8 electrons, hydrogen is going to be happy with 2. It'll be just like a helium on its electron outer shell. Lithium similarly has 3 electrons. It has 1 valence electron because it's in group 1A. And when it loses that 1 valence electron, it has the same electron configuration as helium, a noble gas. So these atoms are going to seem a little bit different than the others, but they're following a very similar rule, the Duet Rule. And for our purposes, it really is only going to apply to hydrogen and lithium, and it's most important for hydrogen. Hydrogen will tend to either want to gain 1 electron, or it might seem surprising at this point, but it might even be happy to lose its 1 electron. But we will worry about that a little bit later. So I'd like to make a little bit of a warning here. When we talk about gaining and losing electrons, this can't happen unless there is something out there to gain electrons from or to give electrons to. There's no magical electron fairy that flies around finding innocent atoms saying, "Here, I bless you with extra electrons," or "Let me take these electrons away from you." No. So, for example, sodium needs to give away its valence electrons. You have to have it given to another element that would like them, like chlorine or another nonmetal. So you need to be very careful that you don't confuse a neutral atom, which has its usual number of electrons, with an ion, and the ions have gained or lost electrons. So for example, when we are talking about, say, oxygen, oxygen is normally found as an element. It's a diatomic element. It has formula O2. That is a far different thing than an oxide ion, O2 minus. Now the focus of this chapter is on bonding, and we're going to explore that, but first let's just get a very general description of what it is. So bonding describes how atoms are going to interact with each other in an attractive sense. So let's look at the two keywords there, atoms. So it's atoms attracting each other, not molecules attracting each other, which will be a different topic, but atoms attracted to other atoms. And we are going to see two types of bonding in this class. There are others, but we'll focus only on two. Ionic bonding, which I'm going to start with, and then a little bit later on we'll talk about covalent bonding. So ionic bonding is the attraction that results between ions of opposite charges. In most cases that we're going to see, ionic bonding occurs between an ion of a metal, and remember metals make positive ions as we just saw, with the ion of a nonmetal, because nonmetals make negative ions. We will see shortly that sometimes these ions could be polyatomic, meaning there are many atoms in one ion, like sulfate, where this 2- doesn't mean the 2- belongs to oxygen or sulfur. It belongs to all of these atoms combined. And something which is negative like this would like to seek out a positive ion. So we'll get to talking about polyatomic ions a little bit later, but I'd like to start with the simplest cases. So ionic bonding of the types that we're going to look at is the strongest of the bonding types. And what does that mean for strongest? To be a strong type of a bond, that means it's going to resist letting the atoms be torn apart once the bond is there. The atoms are very attached to each other. Ultimately, the way we measure this is with melting point. So, for example, ice. We know that ice melts at 0 degrees Celsius. That's a fairly low melting point, although compared to other substances it's actually quite high. But compare this to melting points of ionic compounds. Ionic compounds tend to be much more in the range of 500 degrees Celsius all the way up to 2000 degrees Celsius, although that high is very uncommon. So they are the strongest of the types of bonding. So let's look at some examples here. So sodium chloride, this shouldn't be surprising, a metal and a nonmetal. And this is just plain old table salt that we use when we cook or eat. Calcium oxide, again, a metal and a nonmetal. Copper 2 bromide, I'll explain why I said copper 2 in a moment, but again it's copper and bromine. And lithium fluoride, another metal with a nonmetal. The one fact which I want to emphasize above all others about ionic compounds is this. The formula must have 0 total charge. So the opposite ions, the positive ions, have to be put together in just the right ratio so that the charges add up to 0. Now we're going to call the positively charged ions, that gets very tiresome calling them positively charged ions, positively charged ions. So we're going to come up with this term here, and this term is cation. Not cation, we're not in Louisiana, cation. And negatively charged ions are not anions, they are anions. These terms come from electronics. When we talk about batteries, there's a thing called a cathode and an anode. So cation and anion. So let's look at examples here. Sodium, we already saw, always likes to lose one electron because it's only got one valence electron. Chlorine was in group 7A, so it's always going to make a 1 minus ion. So if sodium is 1 plus, chlorine is 1 minus, it makes sense that these two would come together in a 1-to-1 ratio, because bringing them together cancels out their charge. And so this gives us a neutral ionic compound, sodium chloride. What about sodium and oxide here? Well, oxide has 2 minus charge. Remember, oxygen is in group 6A of the periodic table, so it needs to get to 8 electrons by getting to 2. Giving it 1 sodium wouldn't be enough. 1 sodium would only cancel out 1 minus of the charge, so we need 2 sodiums to combine with every 1 oxide, and that gives us this formula here, Na2O. You'll notice that in any ionic compound that we always list the cation first. There are no exceptions to that. Now, I need to augment those rules just a little bit. We always want to show the ratio of an ionic compound in the smallest whole number ratio. I want you to think back to sodium chloride a second ago. Well, if 1 sodium combines with 1 chloride, couldn't I have said 10 sodiums combine with 10 chlorides? Or 100 sodiums with 100 chlorides? And you see, that could give us a very messy situation, because is it Na1Cl1 or Na2Cl2, Na3Cl3? You get the idea. I could just keep putting any numbers here so long as they were the same. It's 1-to-1. So for ionic compounds, we always write the ratio in its possible smallest whole number form. So for example, when we have calcium combining with oxide, the correct formula would be CaO, not Ca2O2. Why? Well, this isn't the lowest whole number ratio. So what you always need to do after writing a formula is check the 2 subscripts and make sure they're not divisible by anything other than 1. If they are divisible by anything greater than 1, then you need to divide by that number until you can get them to the lowest whole number ratio. So we divide by 2 in each of these cases. Sometimes the ratio is a little bit more complex. Like, for example, if we look at aluminum here, aluminum is always 3 plus, and oxide is always 2 minus, so I can't combine these or it would be a 1 plus charge. The easy way to do this is to do what we call the crisscross rule, which will usually work for most combinations, and it's what I recommend everybody do. You write out the full formulas of the ions, so Al3 plus, O2 minus, and then we just crisscross the numbers. So Al gets the 2 from oxygen, and oxygen gets the 3 from aluminum. Let's make sure that this works. Aluminum is 3 plus. We have 2 of them, so that would be a total of 6 plus. 2 times plus 3, 6 plus. What about oxygen? Oxygen is 2 minus. If there are 3 of them, that would be 6 minus. So 6 plus and 6 minus cancels out. This is the correct formula for aluminum oxide. I would note that we would also want to check at this point that these have any other common divisors, and they don't. The largest number that divides evenly into both of these is 1. So this is in its lowest whole number ratio. Here is where crisscross would not work by itself. Here I'm doing magnesium with a 2 plus and oxygen with a 2 minus, and this goes back to what I just talked about with calcium a moment ago. If we do crisscross, we get 2 and 2, but that's fine. We just have to always remember to ask ourselves, are these numbers both divisible by any number greater than 1? And they are both divisible by 2. So we simply divide both of those numbers by 2, and that gives you MgO, the correct formula. Remember, this only applies to ionic compounds, so when we get to covalent compounds in a little bit, these canceling out of numbers will not apply. So now let's take a look at nomenclature, which means the naming of these compounds. Now, we have already seen that in many of these cases, one of the ions comes from a metal and the other comes from a nonmetal. But before we try to name the compound, we have to ask ourselves a question, and this is something we haven't dealt with just yet. We have to see if the metal produces only one type of charge. For example, sodium is only going to be +1. So the only types of sodium is plain neutral sodium, which means it has no charge, or a sodium ion, which is always +1. So figuring this out is quite easy, although it does involve some memorization. The elements in group 1A, and specifically the metals, so hydrogen is a little bit tricky here, but other than those, the elements in group 1A only form 1+ charges, always. The elements in group 2A only form 2+ charges. Aluminum, which is in group 3A, only forms an ion with a 3+ charge. Some of the elements under aluminum do that as well, but I don't need you to memorize that. So this makes it easy for a lot of different compounds here because the charge is just the same as the group number for those metals. There are 3 other special cases that I need you to know. Zinc only makes a 2+ ion. Cadmium also only makes a 2+ ion, and we won't talk too much about cadmium. Zinc is going to be more important to us. And then another very important ion for us is silver, because we use silver quite a bit in the lab, and it only forms a 1+ ion. Now, all the other metals on the periodic table we are going to assume can make more than one charge. Some people will argue about that. They will say, oh, well, nickel is always 2+, but there are some occasional exceptions to that. So we're always going to assume if it's not on this list here, so group 1A, group 2A, aluminum, zinc, cadmium, silver, that it can make more than one charge. So here we have a summary of those ones that we need to worry about. I've left these guys off because they're radioactive and we're never going to deal with them anyway. So that's why they're not marked off there. And then these are the other 4 somewhat special cases. You'll notice that aluminum is in group 3A, so it has a 3+ charge. And coincidentally, these are in group 2B, so it does turn out that they have a 2+ charge. And then silver here is a 1+ charge. But I don't want you to get the impression that copper up here is always 1+, so that's why we left it out. So essentially, all these metals here and all these metals down here, we are going to assume can make more than one charge. And there's even metals down here, like lead and tin, that can have more than one charge. Now let's look at the nonmetals. In group 7A, they only form ions with a 1- charge. Group 7A, remember, was called the halogens. So 1- is the only charge they will form. The nonmetals in group 6A, which is most of the elements in group 6A, will only make a 2- charge. And the nonmetals in group 5A will only form ions with a 3- charge. The only ones we're really going to be interested there are nitrogen with 3- and phosphorus with 3-. We don't deal much with the elements below that, like arsenic, because arsenic is a metalloid, and then as we go lower, they are metals. So we're only talking about the nonmetals right now. Now, the nice distinction about these anions compared to the cations is that they are never going to form more than one charge. So these values are completely fixed, And we've pretty much talked about all the nonmetals that we need to worry about. So this picture, figure I believe 3.2 from page 79 of the textbook, illuminates essentially all of the ions that you need to worry about, but it does leave out a few. So let's just put those guys in there, even though they're not technically written in the book. So those are the 3 special ones. And these are the anions, which always have the same charge. You might ask me, well, Professor Katroulis, wouldn't carbon be 4-? And the answer would be yes, if it does form an ion. We don't tend to find carbon making ions very often, though. Carbon is going to be a very special element, and it's going to get a lot of attention. More than 4 chapters to itself coming up when we get to chapter 10. So we'll worry about carbon on its own special context. So what I'd like you to do here is I want you to consider the potential formula that you could get for an ionic compound from each of these pairs of elements. Let's go ahead and do the first one together. So let's say we have sodium combining with sulfur. We ask ourselves what the formulas are of sodium's ion and the ion which would come from sulfur. So we look at the periodic table. Sodium is in group 1A, so it's always going to be +1 as an ion. Sulfur is in group 6A, and we saw those are always 2- as an ion. This is not the formula. This is just my work. So now we're going to want to combine these in the smallest whole number ratio. So let's do crisscross. How many sodiums will there be? There'll be 2. How many sulfurs will there be? There'll be 1. So the formula is Na2S. You will notice, and I cannot emphasize this enough, in an ionic compound, there is no charge written down because the charge must add to 0. So these pluses and minuses are gone. We don't see them anymore. I see them in my head. I know that the sodium is +1, but in the written formula, we don't show them. So please take a moment to pause the video and look at the possible pairings of barium and nitrogen, and then calcium and selenium. Okay, I'm going to assume that you have at this point gone and hopefully used your periodic table to help you out in figuring these out. So barium is in group 2A, so it would only form a 2+ ion. And nitrogen is in group 5A, and that only forms a 3- ion. Let's confirm that. Barium, group 2A, is 2+. Nitrogen, group 5A, wants to get to 8 electrons, so it gains 3, so it's 3-. So let's do crisscross here. Barium, you need 3 of them. Nitrogen, you need 2 of them. And I want to emphasize that we need to then check these numbers and make sure that they aren't divisible by anything greater than 1. And so these are both, the common divisor that they have is 1. There's no other thing that divides into both of them other than 1. The same was true here with Na2S. And you know whenever there's a 1 that the only number that would divide evenly into it is 1. So that's why I didn't even check with that one. Selenium and calcium. Selenium is in group 6A, so it's going to be 2-. And calcium is in group 2A, so it is 2+. So here's calcium in group 2A, it's 2+. Selenium is in group 6A, so it's 2-. Now hopefully you were not deceived into putting selenium before calcium, because remember the rule is the positive ion always comes first. So if we did crisscross, we would have calcium 2, selenium 2. The problem with that is those are both divisible by 2. So we divide both of those numbers by 2, and that gives us this as the formula for calcium selenide. So calcium 2 plus, selenium is 2 minus. I'm going to go ahead and end this video here, and when we come back we will start looking at compounds which contain metals which make more than one charge. Thank you.